Hi guys, welcome to this next video. Today we want to discuss calculating the displacement damage using our displacement cross-section expression that we have developed. So in the last videos, we were reminded that the DPA, if we use a very simplistic approach, that is 3.77 for the fission reactor, and this was our displacement cross-section, which I will just write again here. So sigma d at neutron energy En equals to sigma s En over lambda En, and you have the electronic stopping kind of regime, EC over 4 ED plus, and this is the non-electronic stopping regime, lambda En minus EC over 2 ED. Okay. Anyway, so this will account for pKa's of various energies. And yeah. So the energy of the pKa, depending on the energy of the incoming pKa, we will have different numbers of vacancies being created. So how can we calculate neutron damage now? So first thing, if we want to do something very formal, we'll need to look at the rate of interaction of displacement, and based on that, there is n sigma phi. Okay, so this is the number, this is the displacement per unit volume per time over volume times time. This is the atoms per volume. This is the cross section, and this is the neutron flux. All right. And if you want to have a DPA, all we need is RD over N. So we have a displacement per volume per second, and then we'll have divided by the atomic number density. So this will give us the DPA per second equals to sigma d times phi. Okay. But we know that neutrons don't just come in at one energy, so we'll have to account for that as well. So dPA per second equals to some integral of phi d En, phi En den. So this is the proper expression. And what are the limits? Again, we will have some lower limit. We have some upper limit. Of course, the neutron can come in at hypothetically infinite energy, but of course that doesn't happen. But we'll just have the maximum neutron energy here. Okay, and what's the lower limit? Well, based on the conservation of kinetic energy and conservation of momentum, we will have this expression here, Ed over lambda. Why is that? Remember that Ed equals the minimum energy of the pKa to generate one displacement. Alright, so that's the minimum energy to generate one displacement. We're having a neutron scattering back at 180 degrees, and this pKa will have this energy Ed. What will the energy of this neutron be like? Okay, so we are taking the minimum energy of the neutron, right? So the minimum energy of this neutron to generate this energy Ed, it means that this neutron will have to backscatter 180 degrees to generate this excuse me, this energy, this pK with energy ED. Yeah. So how do we calculate this? We'll have En equals to, or rather T equals to lambda En. Okay? So if T is ED, so this is coming from our conservation of momentum and kinetic energy. So the energy of the neutron here will be ED over lambda. So lambda is some factor to tell us how much energy is transferred to this pKa if this thing is backscattered 180 degrees. So that's where you get the ED over lambda from. Now, if you want to calculate this, this is to take in the energy of the neutron. This takes into account energy of neutron, and of course the various scattering of pKa. So this is the dPa per second from ED over lambda to infinity. Now this is the most accurate way, or one of the more accurate ways of obtaining our dPa per second expression. ED over lambda to infinity sigma dEn phi En dEn. Okay, I think there's a mistake here. This should be sigma. Okay, so from ED over lambda to infinity, sigma dEn phi En into dEn. Okay, so to do this, we'll probably need some numerical integration. Either that, or we'll have to have a mathematical expression of this. And at this moment, we don't really have something of that sort. We may have a distribution, but not a mathematical one. We can do some mass fit curve to find out this phi En, and then we'll just substitute our expression, this into the integral, and let the computer calculate it. Okay, so that's the most accurate way. Now, I don't really have a distribution with me now for this, I mean. But what we can do, again, if you don't have that, is just to assume all neutrons coming at 1 MeV. But if you really wanted to do the accurate way, we'll have to use this expression over here. Okay, so now let's just assume single neutron energy. Okay, 1 MeV. So we have, again, already derived the expression to do the so-called full-fledged calculation. And now let's do the simplified calculation. Let's see how this, how the pKa scattering at various energy will affect the dPa. So, let's assume phi 1 MeV is the same. 3.11 times 10 to the 13 neutrons per cm square per second. Okay, and ED, we'll just assume 35 electron volts, same as before. Sigma scattering based on NNDC. That's about 2 to 3. Okay, let's just use 3 barns. Yeah, we have used, let me check. Yeah, we have used 3 buns before to calculate the cross-section. Okay, so we'll use the same amount to keep things constant so we can have a decent comparison. Okay, so 3 barns. 3 times 10 to the minus 24 cm squared. Okay, so now we have this, and then we have En equals to 1 MeV equals 10 to the 6 eV. Now we can substitute all this into a displacement cross-section. So, just going to calculate the displacement cross-section now. So that's 3 barns. 3 barns, okay, 3 barns over lambda. Now what's lambda? You haven't calculated that yet. Lambda equals to 4 over 56. Okay, so I'm just going to substitute that in. 4 by 56 into the 10 to the 6. And then I'm going to multiply that into a bracket below. EC. What is EC? Again, we've discussed before, that's about 56 kilo electron volt. Slightly lower than that, but 56 is an easy number to remember. So 56,000 EV over 4 times 35. Okay, plus EC, 6,000. Lambda En, 4 by 56 into 10 to the 6 minus 56,000. Okay, so I'm just substituting here, and that is divided by 2 ED. So the units should be fine, they should all cancel out, they're all in EVs. Now, after plugging in Excel, let's find the answer. So I'm just going to punch these numbers in Excel for a minute. Okay, so 56,000 divided by 4 divided by 35. So first term here is 3. So 400 is the first term. That denominator is 4 divided by 56 times E6. 71428. Okay. So let's calculate the second term. 56,000 times bracket 4 over 56 times 10 to the 6 minus 56,000 divided by 2 divided by 35. That's a really big number. Okay. Oh, I think I forgot something. This is a EC squared. So this shouldn't be 400. So these are really, really big numbers. First one is 224. Whatever number of zeros that is. And the other one is 1, 2, 3, 4, 2, 8, 5, 7. Just substituting numbers there. And then all we have to do is sum these two numbers up and divide by the denominator here, and then we times 3. Okay, we will have a displacement cross section of about 1459. 1459 barns. So let's have a dPa per second kind of thing. Okay. Let's calculate a displacement rate. Okay. Let's use dPa per second equals to 3.11 times 10 to the 13 times 99.2 times 10 to the minus 24. Okay. Neutron per cm square per second. This is in cm squared. So this is 4.538 dPa per second. So this dPa here, 3.77, calculated using earlier approximation. How many years was that? I'm just gonna check. That's a 5-year period. So we assume a 5-year period. So this is done in a 5-year period. So let's use the same 5-year period. 4.538 10 to the minus 8 dPa per second times 5 years times 365.25 days per year times 86400 seconds per day. 5 times 365.25 times 7.16056. Okay. So we can see that if we take into account, okay, this is in 5 years. Okay. So this is also in a 5-year comparison. So if you have to account for the pKa direction, if you were to account for that, the dPa will increase. So this is based on kinchin-pease and isotropic scattering and 1 MeV neutrons. Alright, so that's one of the things we have to take into account when we calculate neutron damage. But since don't have the correct so-called spectrum and computer program, we'll just leave it as that for the fission discussion. Now, just for interest, let's take a look at the fusion spectrum as well. Okay, let's assume they all come in at 14 MeV. Okay, we assume they come in at 14 MeV, and then we find that sigma scattering, that's about 2 barns. If you go and look at NNDC, it's about 2 to 3, but I'm taking 2 because at about 14 MeV you can't really see anything that goes above, that goes to 3. Okay. So 2 barns if it's hitting iron at about this high energy. Okay. So if we were to do something similar, we can just calculate the displacement cross-section using the same formula. Okay, we have all these again, now except that the energy here is a lot higher. So I'll put 2 over 4 over 56, 14 times 10 to the 6, okay, times 56,000 squared over 4 times 35 plus 56,000. Okay, 4 over 56 times 14 times 10 to the 6. That's over 2 times 35. Okay, let's calculate. So the first term, nothing's really changed. The second term here, okay, yeah, second term will change. In this first term, this denominator here will be about 1 million, 10 to the 6. Okay, second term here will still be 224 with 5 zeros at the back. Second term here will be 7552 with 5 zeros at the back. Okay. And all this will be multiplied by 2, and we have a displacement cross section of 155.2. Okay. PA per second will be you get this number. And the dPA after 5 years, I'm going to use the same formula. Now that will be equal to 7.631. Now if you look at these two numbers, they look so similar that you think that fusion neutrons don't really cause that much more damage. But in actual fact, we will have, if you look at papers, I'm going to put a PDF in the description. If you look at something like ITER, this is the ITER experiment for fusion. The damage is as high as 15 dPa per year. This is 5 years. So why is there such a big discrepancy? Well, at high neutron energies, let's say 14 MeV, okay, and then it starts to hit iron 56. What can happen? There are two things that can occur. Three things. Firstly, scattering. This is the standard pKa reaction we're talking about. Secondly, N-alpha. Thirdly, N-proton. So where did these two come from? Now, see, the thing is that the neutron is supplying so much energy to this nucleus that it can knock off a whole alpha particle. And this alpha particle is charged and it has high energy, So it's going to create lots of collisions, and that's where all the extra pKa's will come from. So these are the other reactions that can occur. Okay. So you may need more new equations to describe damage in fusion scenarios. And of course, there are other phenomena that occur like inelastic scattering. Okay, this one is another can of worms, but the scattering we are talking about before is elastic scattering. That's the hard billiard ball models. So there are new equations that need to be described. And the equation we have developed before for the displacement cross-section is not quite sufficient. Maybe we'll talk about this in some other video, and it's more challenging to try and derive such an equation, seeing how many reactions we have to account for. Well, for now, I won't do it till further notice. So that's all I have now. So we have discussed how dPA, displacement per atom, is actually calculated. And hope you have enjoyed this video and it was informative to you. So thanks for watching. I'll see you guys next time. Bye bye.